So we learned um, the column space. The other important subspace of a vector space is the null space. Uh, Understanding null space is a little bit easier after we understand column space. So we established that um, when singular matrices project the input samples to input vectors to its column space, whole bunch of vectors they go to zero, right? So let's it is going to become more obvious when we play the animation here. So we know, like, this is an animation from a few weeks ago. So this is a singular matrix with columns 2, 1, 4, 2. Whatever the input is, we know that the output is going to be on that line for sure, like whatever the input is. So the output is going to be a linear combination of the columns of this matrix, which is the same thing. Like the second column is the linear combination, a multiplied version of the first column. So there's only one space, one line that this matrix sends our vectors to. Like all of my purple, green, and red vectors, they go live on that space, right? Except for the purple, because purple, I took purple intentionally, so we know the red and green one, they go to that space. And if we play with all of the points, so all of the points, they go squeezed into this line. And this is important because if you look at one direction. So this is important to notice that everybody goes to some point on that line, but one direction, the direction with the purple, uh, they all go to zero. So this is important from the linear algebra perspective because you start with something non-zero and you multiply this input with some vector, some matrix that looks non-zero, and your result becomes zero. So the direction, the set of vectors, the direction, the space spanned by this direction is called the space spanned by this by the vectors who get projected to zero as a uh, as a product of this matrix multiplication is called the null space of this matrix. So some points again about the null space. A good description of null space is of a matrix A is the span of vectors x that gets to be projected to zero, meaning ax equals zero, um, makes the null space of the matrix A. So obviously, this is obvious for invertible matrices. There's only one input x that goes to zero, which is the zero matrix. But acknowledging that a set of vectors that gets drops to zero is important. One thing that I would like to mention here is that you see if matrices are projection um, functions, like that takes a set of vectors from the domain vector space and then sends them to a target vector space. Notice that the column space is in the target vector space, and the null space is the set of a subspace of the domain vector space. A good representation is here by the legend himself, Gilbert Strang, four fundamental subspaces. You see here we are talking about a target, so a domain vector space here in n-dimensional vector space. And this vector space, by the virtue of getting multiplied with a, so I make this operation ax equals y, and x's live in the domain vector space, and y live in the target vector space, which makes my a a matrix of m by n. So I will have to have m rows because my output, my y, is in m dimensions, and my number of columns have to match um, my domain vector space. So let's start with the column space. I know any vector in this space, which is the row space in the domain, gets projected to the column space. So we saw that if it is if it is singular, whatever you do, like your matrices are going to live here. So this is the living space of your output, right? And your vectors here in the row space, they go to some other vector in the column space, which is an m-dimensional, which is a subspace of the m-dimensional vector space, R to the m. R to the m is like everything in R to the m-dimensional R, but the column space is a subspace of that. Alternatively, a whole bunch of vectors in the null space. If this is singular, a whole bunch of vectors, everything that live in the subspace, they go to 0. So let's make this 0, this point 0. So like everything goes to 0, and everything in the row space, they go to the column space, and all bunch of vectors in the null space, they go to 0. They go to hell, right? Similarly, there is so the row space definition of the row space is obvious, and a column space is at the target. And notice how the null space is a subspace of the domain, the source vector space, and there's a left null space, which is the null space of the A transpose, meaning all bunch of vectors that live in the target that go to 0 in in R to the n, like all bunch of zeros, n number of zeros in the source when you do A transpose X equals Y. Because when you do A transpose, you know you will have n number of rows in A transpose, and so that's the left null space. So that's the 4 fundamental subspaces. Let's go and understand how to find the null space. 3 steps involved in finding the null space is first, again, just like the column space, we're going to find the raw echelon form using Gauss-Jordan of a matrix and find the free variables that don't have pivots, and we'll set AX equals 0, right? We'll find through this. Again, let's look at our matrix here. So it's a 3 by 1, 2, 3, 4, 5, 5 columns. And let's understand the domain, right? The input. Input has to be 5-dimensional. So this matrix takes 5-dimensional vectors as input and yields 3-dimensional outputs. So the column space of this one is going to be at most, we know at most is going to be 3. It might be lower than 3. It might be, we will see. We will find a column space that has the pivots, and those that are not in the column space will help us understand the null space. And again, the null space, let's remember the null space was a subspace of the domain, meaning the input. Our inputs are 5-dimensional. We don't necessarily say that it is all R to the 5, but a subspace of R to the 5, 5-dimensional, a subspace of this R to the 5, meaning its span, its basis set is going to be represented with 5-dimensional vectors. is going to give me the null space of this matrix. So let's go and try to find its row echelon form. So if I zero out, if I make these guys go ahead, and then by doing the Gauss-Jordan elimination, I find this row echelon form. So I know, you see, like, after I'm done with the whole Gauss-Jordan elimination, since this is not a square matrix, I don't necessarily a end up with an identity matrix, um, and because some matrices, some vectors are going to go to zero, because I am going to a lower dimensional space than the input space, right? So I know the first three columns are my pivot, and the other two inputs, meaning in my inputs, remember so this is my matrix, and I put my input here. So x1, x2, x3, x4, x5. And when I do the inner product or matrix multiplication, the first three have the pivot, and I know the last two ones, x3 and x4, are my free variables. So what am I going to do with these x3 and x4 free variables? I'm going to find the null space using the x3 and x4. So let's go ahead and so like we found the free variables, and we're going to write the ax equals 0, 4, like which axis, which inputs are going to give me this form using the free variable. So I know this is my input. So I can do this matmul, right? So like I'm talking about three, so this is a linear set of equations. I would like to find my x such that it is going to give me this. I know my input is definitely not all zeros, but my output is all zeros, and null space is defined as such. So I'm going to represent, so this is my ax equals 0, then what is x in sense of the free variables. So that's the task that I'm trying to solve for. And let me write. Like this, write this into a linear system of operations, equations. So I have three rows here. So three rows each multiplied with my variables. So if I multiply them, 1 times x1 plus 0, 0, 5 times x4 minus 3 times x5 is equal to 0. You see that this is like, here I did nothing. I just wrote this matmul, matrix multiplication, matrix vector multiplication. So next thing I'm going to do is I would like to leave my so I would like to have a vector looking thing. I would like to leave my x1 here, x2, and x3 alone. I would like to take my free variables to the other side. So how can I do that? I just send these guys to the other side of the equation. Because after all, we know algebra. We know the high school algebra. We can take the ones to the other side of the equal sign, right? So I have my x1, x2, x3 is equal to this form. So then I can actually, so this form of inputs. So let's remember what we are trying to do. We're trying to find a null space for this matrix. We're trying to find the set of vectors that goes to 0 even though they are not 0. Like, and there's no number here, so all of these vectors are going to be represented with respect to my free variables. So I'm going to go ahead and rewrite this, but I'm going to add x4, x5, append x4, x5 at the end. So like this was x1, x2, x3 equals to this guy was what I found from ax equals 0 equation, and I am able to find this one. So then I can write this into as summation, right? So I have all this part equal to like my x. So this is my x, which gives me ax equals 0. And I was able to write my x, the vector x, as as a function of my x4s and x5s. So I can write them like it's an x4 times this plus x5 times this. You see, when I make this happen, x4 negative 5x4 plus 3x5 the first row, and 0x4 plus x5 the second column, yada yada yada. So this guy makes my gives me the form of x's that give me 0. And my dear friends, this gives me the basis of my null space. So I can say my null space is then is the span of these guys: negative 5, 0, negative 2, 1, 0, and 3, 1, 1, 0, 1. And I can go ahead and check. I can put down my basis, just the basis, the 5-dimensional basis in my original matrix, and I get 0. And the other element of my basis, I get 0. And not only them, I can use any linear combination of these basis functions, basis vectors. And if I use them as input to my 3 by 5 matrix, I will get 0. Why? Because it's called a space. It's called a subspace with bases defined as these two vectors, and its dimensionality is 2. It's actually a sheet of paper. It's a two-dimensional paper on a five-dimensional world, right? So I can walk on that space with only two numbers, but I know where this space is. So that's the null space represented by the basis of this null space. So using this null space, I have an understanding of which vectors go to 0. In a video that will come up, I will explain. We will go through an example of how the null space becomes useful in an application.